Okay, here we've already defined what the factor, treatment, experimental unit, response variable, and type of study are. And we have the population mean, and the hypothesis and the assumptions are all set up. So now here is the sample data. Number of units produced per week using method A, method B, and method C. Now we have to develop the analysis of variance table so that we can do the test, and for that we have to set up some minimum initial statistics. So we need the count. So that's our sample size, and for a one factor analysis of variance, the sample size need not be all the same. It could be different. Now sample mean is the average, and sample variance is var dot s. Okay, so these three can be copied over. So method A, method B, and method C. Now the overall mean, x double bar, is the average of all of these. Now if the sample size are same, we can just average the averages and that will work. But suppose if the sample sizes are not same, then we have to weight them. So first let's look at it in two different ways. You go back to the original data and find the average of all of them. So you could do that. So that would give us the overall mean. Or if you want to compute x double bar using the sample means, then you have to weight each sample mean by the sample size, and then you have to divide by the total weight. So weighting them can be done using a formula called sum product. So you take the sample means, comma, the sample sizes. The sum product will multiply each sample mean by the sample size. So 5 times 62, 5 times 66, 5 times 52. So that's what the sum product will be, and then add them up. Then you divide by the sum of the weights, which is the sample sizes. This will give us x double bar. So this is a generalized formula. This formula will work whether the sample sizes are all the same or not. Yeah. Same here too. You can average all of them, and that will give you the sample mean whether or not the sample sizes are same. Now K is the number of populations or number of treatment factor levels. So we can do that using count A and count the number of methods. We need to do count A because this is non-numeric. Count will work only if the cell contents are numbers. So if cell contents are not numbers, then to count how many are there, you have to use count A. Now n sub t is the total sample size, and that's the sum of the three sample sizes. So that will give us the total sample size. Now let's compute SSTR and SSE. So SSTR is for each sample, take the x bar, subtract x double bar, and square it, and then you have to multiply by the sample size. Okay, so let's do this one part at a time. Let's not put everything together in one big formula, and that could be confusing and very easy to make mistakes. So here we'll go x bar of that sample minus x double bar. Now x double bar must always come from B36, so that has to be absolute reference by pressing the F4 key. Now we need to square that. Now we copy that. Okay. So now the SSTR, then we'll multiply the squared difference between x bar and x double bar with the sample size. So n sub j times that. So that's what this is. N sub j times x bar sub j minus x double bar squared. Now we copy that across. Now if you sum these three, that is SSTR. So that one is SSTR. So let's put a box around it. So that's our SSTR. Now SSE is n sub j minus 1. So that is sample size minus 1 times the sample variance. Sample variance is right here. Again, we will do this one sample at a time and then add them up. So that will be n minus 1 times the sample variance. That is for the first sample. Now we copy that across. Okay, and we sum. This is the sum, so we can copy that down, and that will give us the SSE. So now we can put all of these here. So treatment is SSTR. So sum of squares will be SSTR over there, and SSE is here. Okay. Now treatment sum of squares is k minus 1. So that is k minus 1. And error degrees of freedom is n sub t minus k. So that's n sub t minus k will give us the error degrees of freedom. Mean square is sum of squares divided by degrees of freedom. That's our MSTR. Now sum of squares of error divided by its degrees of freedom will give us MSE. Okay, let's decrease the decimal places here. So that is our MSE. Now the F calc is MSTR divided by MSE. So that will give us the F value, and the P value then for the test is F dot dist dot RT of that F, comma, the 2 degrees of freedoms. Numerator degrees of freedom, denominator degrees of freedom. Now let's express that as a percentage. So that gives us the ANOVA table. So this is what we call as ANOVA table, analysis of variance table.